Yes. So, as Ronald mentioned, I'm an alumni of this university. So I studied here 20 years ago. I finished my PhD, and I'm doing practitioner work as an enterprise architect for about 20 years now. And on the side, I'm working on this platform with the aim to be able to create apps using natural language. And I have to say, a lot of the stuff you're reading in the articles is the foundation of how we're building it. So it's nice to see that you're also learning about the foundations. But today we want to talk about the latest hype, artificial intelligence, generative AI, and of course, well, you probably all are all using it every day, and it's cool stuff. I mean, it gives you a natural language interaction with a system with that kind of knowledge. It's cool stuff, of course, and it's nice to have a natural interaction with a system, and it gives you access to a huge amount of knowledge, and you get personalized output. So you ask questions and you get tailor-made answers. So that's all very nice, but you probably also experience the downsides of large language models where they don't have logical ability to do logical reasoning. It's not very transparent how they come up with their answers or make decisions, so it's basically a black box. And of course, hallucinations are something we all experience once in a while. So it's not as accurate as you would want it to be, and especially for enterprise applications, these are really risks. And there was a recent MIT report that stated that 95% of all the pilots using generative AI in companies fail. So is there an alternative way to approach AI? And the title of the guest lecture is Intelligence Only Comes After True Understanding of Language. And this is something both John and I feel is the key to an alternative approach. So on the left you see here somebody giving an instruction to an AI agent. And first, if you want to, as an agent, if you want to execute the instruction, then you have to understand what is the instruction exactly about. So that is where natural language understanding is the first phase of true AI. And only after having clarity about the instruction can accurate and reliable actions be taken. So this is a sort of a two-phased approach where we both are working on together, where we feel it gives a path to AI where you still have that natural feel on interaction with an AI system, but it does exactly what you want it to do and nothing else. So I'm going to talk a little bit about natural language execution, the blue part on the right, and John will tell you everything you need to know about natural language understanding. So what is natural language execution? So it's a form of AI that delivers directly executable deterministic decision-making systems. And they are based on controlled natural language input. So that's later on in this course. You will learn also a little bit about controlled natural language. And this is a way of specifying an ontology and business rules for the AI agent to execute. So this is the intelligence. It's a deterministic system, so every time you give it the same instruction, it always does the same thing. There's no hallucinations or whatsoever. And it's directly executable. So there's no code generation involved. And this is what most of the things like Copilot or other large language applications that allow you to fight coding, applications that allow you to build software, they always generate code. But with code comes a lot of debugging stuff, and this is something that makes it very complex in a longer term to maintain such an application. So, as Ronald mentioned, I'm a founder of a startup. It's called Hapsah. It stands for Human-Aimed Platform for Semantic App Hosting. And it's a way of building applications, giving in natural language, controlled natural language input. But of course, we also, not everyone is textual oriented, so modeling, visual orientation is for a lot of people also important. So it's basically a modular environment where you give in the ontology of your application. You can also use REST API, so it doesn't need to be the modeler itself. You can also, if you already have for instance, an OWL ontology, you can import it, so you don't have to do things from scratch, but modeling environment is also a way of building applications. As soon as you have it available in the modeler, it's there in runtime as well. So the application is instantly there, and there's no code generated. And then you can use the application, and of course also through the screens, but also through an API. It's an event-based system, so every time new data goes into the system, events are generated to publish to other applications. So you can create an event-driven architecture if you want. So what does that look like? Now I have to switch to the video.
Just keep going. Just click.
So this is what it looks like. You start out with a clean sheet, and you want to build a very simple application where you want to keep track of which person is driving in what kind of car. So of course we need an entity type called person, which is in fact an agent of the human species. You always have to give in names in singular and plural, and a definition, so semantics are important. Because it can always give user the feedback, what kind of entity type am I dealing with. So we created a thing called a car, and now we want to add an association that says person drives car. So here we're giving in singular and plural form the definition of the association, and also the backward way of expressing the association. So we're going back to the model. We've got a person as an agent and a thing, a car, but the relationship is not connected yet. So this is where the controlled natural language comes in, and we create simple statements. This is subject, verb, object kind of statements with cardinality, and is it a possible or a mandatory relationship. And now you see the relationship between the two concepts. But these concepts don't have attributes yet. So I want to be able to give the person a name. So we're adding an attribute that's saying a person is always referred to by a name. And backwards, a name doesn't need to be something that refers to a person. You can also use the same name for a thing, for instance. Car, the same thing, of course. Normally you take a license plate number, but here we're taking just for a simple application a name for a car. But you can also, of course, say the brand of the car, the type, the color, whatever kind of attributes you want. So now the ontology is available, and you can see a person is referred to by a name, and it drives a car. So this is a very simple ontology. But now you go to the app, and it's instantly there. So we can create a person, in this case Mr. John Doe, a well-known person, and he's driving a Ford Mustang. That's the favorite car of my son, so I took that one. And now we have two separate instances of a person and a car, but they're not connected yet. So now we're connecting, and it says now that John Doe drives a Ford Mustang. So it's a very trivial application, of course, but it is to show you how it's possible to, from modeling and ontology, have instantly an application available. This doesn't show the, no, it's running again. This doesn't show the business rule part, but somewhere in the next lecture, I will have some time to explain a little bit more about that part of this platform, and also the theories behind it. So again, I saw a lot of the articles you're reading is actually the foundation for this kind of technology. So why is this so important to combine? As I said, this is only possible when you have a proper understanding of the domain. And this is where a lot of domains are described in documents or are in the knowledges in heads of people. And they find it quite hard to express that kind of knowledge in a controlled natural language. That's not an easy feat. So we're working together to see if it's possible to have a more fluent way of expressing knowledge and then translate it to controlled natural language where you can build applications in this kind of way. So this is the combination where the good sides of natural language processing and understanding are combined with the positive sides of natural language execution. So I want to hand over to John, and he will explain you everything about natural language understanding.
Excellent, thank you, Ben. Chances are I won't be able to cover absolutely everything about NLU in the time that's available, but what I'm going to try and do is show you some of the theory and then some of the examples. Where that came from was back in the 1980s when I got really excited about how languages work, how brains work. I had a professor who said we're never going to understand brains because it's way too complicated. And so my life changed at that point. I actually spent time in the library learning everything I could about neuroscience and psychology and philosophy and linguistics. And since that point, I've never stopped learning how the brain works and how we can exploit that with language. And NLU, which I'm probably going to use today because normally I have to say AI because people don't understand what I'm talking about, but I figure from this audience we just talked about NLU and NLE, and so we can just continue that way. We've got the next generation of AI. I like to just start that off, start that message off because the current generation is all about generative AI, and it's been very successful since 2022. But the next generation will, in fact, understand what it is we're interacting with. So, what am I going to try and cover? The frame problem. Have you guys discussed the frame problem of AI? Basically, it's the challenge that if you're a robot in some environment and there's a million possible rules that you have to apply, it can take too long to apply all of those rules and then find that you've got no answer. So in language, when we're speaking, I'm assuming that you're understanding me. I'm talking pretty quickly, and yet the number of things that you can do in this available time, according to MIT back in the 1980s, it's impossible. We can't solve the problem. So I like to use the concept of immediate common ground and general common ground. I'm going to try and keep my terms to a minimum. Immediate common ground is the context of this environment. So we're in a lecture room, I'm talking, you can't rely on anything that you knew before you walked in here. But I can add general common ground, which is background knowledge if I want, and I can introduce, say, Barack Obama, so US President. And I've just given away which Barack Obama I'm talking about. It could be my neighbor, who might be named Barack Obama, but once I say the US President, I'm narrowing it down and I've just brought that into immediate common ground. So there's the current context and there's all your background knowledge. The goal of NLU is to convert it into a natural science. So when Noam Chomsky talked about how languages work, he came up with a bunch of rules and you just apply those rules with parts of speech. So I'm going to give you all of the reasons why parts of speech and those sorts of rules weren't effective. And I believe that the solution to robotics is actually covered, it is actually necessary to solve AI. So is AI solved? Everybody? Nobody thinks it's solved? Yeah, okay. So we got nobody. So this is going to be pretty quick. So when you walk into a bank and you just say to the robot that's waiting for you, can you please transfer $1,000 from my father's account to mine? Nothing happens because it doesn't understand. The same with if you go to Amazon and do shopping, it doesn't work with you just talking to it or typing what you want. Self-driving cars, by 2020 we'll definitely all be using self-driving cars. That didn't happen. Speech, if you look at captions that are automatically generated, there's lots of errors in it. Pretty close, you know, rhymes, but it's not solved. And in terms of looking at a representation of everything on the internet, there is no lossless way of viewing that. So there's something being lost when we compress it into artificial neural networks. And common sense and generalization doesn't work. So the bottom line is that statistical AI is in crisis. When Sam Altman is saying that we've got artificial general intelligence in 2025, he's panicking now because it's not happening this year. And when we're talking to people in government in Australia, we like to use this slide. We're pointing out that with generative AI, we're a little disappointed that all of the countries in Southeast Asia, so this is my Australian accent I'm getting you here. So Australia's looking at putting a couple of $1 billion into generative AI, so building data centers, building power plants, setting up water cooling distribution systems in order for Amazon and Google and other companies to come into Australia and run their AI services. But that's unsustainable. We just had a world that has spent the last 20 years getting rid of everything that uses power, and now we're going to use up all of that power and more with generative AI. So it's not sustainable, it's using our IP, it creates errors, which means that's how you get to that 95% failure rate, according to MIT. Costly and biased, so you don't want errors that are being introduced because the people that create the system are skewing things in a particular direction, politically or otherwise. So all of those issues are in my book. I should probably point out my book because I won't point out my book. I don't have.
Or you'll need one.
Oh, yeah. So this is the book where last year I was just trying to work out what it was that actually made the work I'd done for the last 40 years relevant. And this sort of goes through all of the key points of what's the brain doing, how can you get away from the problems that we have with computers. And as a computer scientist, in 2006 I left full-time work and I just tried to sit down at a computer and write a machine that understood language. And remarkably, I couldn't do it for quite a long time because, you know, where do you start? And that where do you start thing comes back into how do we build robots? And so the problem is known as Moravec's paradox. So Marvin Minsky, Rodney Brooks were pointing out in the 1980s that the things that people can do easily, like we can walk and see and speak, are really hard for machines, and the things that we find hard, like memorizing the entire phone book or memorizing a book, are easy for machines but not for us. And that problem is still here today, and my argument is that until we solve that problem, we're not going to have AI that works like we do. So this is the example of the challenge of the frame problem. So we've got a universe. So you can imagine the universe goes in all directions for many, many billions of light years. And there's one point, one atom that we care about. We're focused on that atom. And yet, you probably noticed that plus sign going across the screen. So how would you write a program? Now, if you wanted to use machine learning, you could train that plus sign going across, and then you could train the plus sign going from the right side to the left side. And there's an infinite number of ways of moving the plus sign. And when you're finished with that, You can then go and add circles and squares and people's faces. So in order to capture all of that with machine learning is an infinitely large problem. And then here's another problem. The plus sign's going down. So the challenge of robotics is to work out how can you do this all in real time. It's the frame problem. So large language models have fixed the frame problem. So if you want to get all of the world's documents into one neural network, all you have to do is run GPUs, so parallel computers, millions and millions of them, to keep pushing all this stuff through your processing engine. And that's great, but it creates this problem of lack of sustainability. And the thing that people have been saying for decades is that the human brain is just not paying attention to the things that we don't need to pay attention to. So if I wanted to walk out the back door, part of the frame problem would be, do I just walk straight there? And as I do, I hit the chair and then the table, and then I'm climbing across. So I can't do it that way. I need to think about going that way and this way to get out. I'm assuming that's the door. To get out that back door. And that's what the brain seems to do is simply choose the right element and continue. So let's have a look at state-of-the-art solutions. When I wrote the book, the thing that was most obvious is if you ask somebody what a brain does, they'll probably say it's like a computer. Does anybody have a different brain model that's not like a computer at all? No hands, just for the people that are watching wherever they're watching. So in every single field of science that I can think of, we know everything. You know, if it's biology, you can look with devices and you can see molecules moving around and you can predict what's going to happen. But in terms of the brain, it's the final frontier in science because people will say it's a computer, great, and then if you read what people think the brain's doing as a computer, there's no way you could implement that. You know, your eyes are picking up something, it's encoding it in some way we don't understand, it's then sending it around to parts of the brain to do things that we don't understand, then it gets consolidated into memories that we don't understand, and then we move, which we also don't understand. So there's a better way of thinking of it as just a bunch of patterns, with all of our brain material is recognizing these patterns and then using them in a very specific way. So it's the final frontier in science, that was the point. So I'd like to find somebody that's got more credibility than me. I mean, I'm just a guy that has been working on language systems for the last 40 years. But there's people like this guy, Tom Dietrich. He's based in Oregon in the US. And he's a machine learning guru. So back in the 1970s, he was using machine learning with computers to do amazing things that we didn't know he could do. And then in the 70s, 80s, 90s, he continued with the expertise in machine learning, deep learning. And when OpenAI had that amazing breakthrough in 2022, you probably remember that everybody's really enamored with the fact that AI has now been solved. He went around the US to universities and this is one of his slides, and he was pointing out that there's actually flaws in LLMs. And I think he summarized it beautifully. They're statistical models of knowledge bases rather than knowledge bases. So if a machine's going to hallucinate or produce the wrong answer, as I would say, it's doing that because it doesn't have a representation of what the answer should be, because there's statistical models of knowledge bases. And the solution, which is really good because I've just spent many, many years writing programs that can recognize language. You want to separate linguistic skill from world knowledge. So you want immediate common ground split from general common ground, background knowledge from the current episodic memory. So we've got episodic memory and create and update world knowledge. So he's sort of describing what you need to do in order to build a robot or have an intelligent machine. And at the bottom he says there's many details to be worked out. And the good news is I can tell you what a lot of those details are today. So let's start with something a little bit fun. Let's look at the world's best robots. This is in China, in Beijing earlier this year. And this, I would say, is not quite human level. And sorry there's no audio, but maybe you guys on Zoom are getting lots of audio. So what's happening is we've got these little fellas. They're not completely human-like, is the way to put it. And here's a goal! Yay! So if I was going to compete on the international stage, I'd want to be competing against these guys at the moment, because they're doing some impressive things, but it could be better. And it's already been done better. Here's a machine that is vastly superior. It's a dog. So what this dog's going to do is recognize that a ball is something that it can chase. It's just turned around 180 degrees. It's locked onto the ball with its vision, and it knows that the ball's not going to turn into a brick or something that's going to hurt it. It's caught it, and now it's going to start doing a victory lap. And it can do that all day without ever falling over. It can do it with a red jumper on. It's, again, doing the victory lap. And this is a full 180-degree turn. You see the eyes are turning around to lock onto the object that it needs to get. It's like poetry in motion. And all legs are off the ground. It's caught the ball. Now it's landed. It's going up quite a steep hill. You may not be able to see that. And so why can't we emulate this? Why do our robots not do this? And we're using supercomputers to drive the latest robotics with machine learning. Why don't we have that? And here's its competition. This is the west coast of the US, Portland, I think. These guys are humanoid robots. There's what its vision system is picking up. You'll notice it's not quite human level. And the challenge, I'll just point out something. Notice that as the Tesla robot here is putting an egg down, it's got some touch sensors in its fingers, but it's going to drop it there. Right? Did you see it just drop the egg in position? As a human, if you're going to put an egg into an egg cup, you sort of push down and you can feel it's in the right spot so that it doesn't break. You don't drop it from half an inch or something, because it's just not how it works. And I recommend you don't do this at home. That's quite... So there's some companies here that have spent hundreds of millions of dollars to develop their robotics, but there's something missing. So here's a thought experiment for you. So you build ontologies in this class. How would you represent 5 of your friends talking together in some nice room with a fireplace in the background and, I don't know, the Alps or something out through a window? That's the challenge of the things that we as human beings do all the time. How would you describe this room and keep track of all the people that you know and what you know about them at the same time? So you can do it with databases and entity associations, but that's hard yakka. Difficult, sorry, that's maybe an Australian term, hard yakka. And if somebody you know walks into the room, they don't walk in as a null entity and then you just start describing them. You recognize them, you know the experiences you've had with them. All of that needs to come together as part of this. And the representation is obviously not like a computer. And again, when the dog's chasing that ball, it knows that it's not a brick because it's trying to catch it with its mouth. And if you played that game and it turned into a brick, it would have a problem. And so that's the level of context that animals already have. So animal brains are already doing the hard part of AI. And we're not emulating it now because of a scientific problem.
John, you've got 10 minutes till the break.
Okay. So when I'm talking to normal people, not experts, not experts at university, when I'm talking to normal people, say in a library, I'll often use these slides just to give them a feel for what the challenge is of AI, because most general people around the world know that AI is all solved and we just have to wait until it starts replacing our jobs. But it's not going to. And here I've looked for 1956 AI Dartmouth, so this is where AI was created. Here's the guys that were there: John McCarthy, Minsky, IBM, Bell Labs, and other notable attendees included Alan Turing, which is remarkable. Anybody can think of why Alan Turing at the 1956 event was probably not there? So what I did was I took the AI version there. There's your LLM output. Here's the Wikipedia output. So he died in 1954. So 2 years before the event, he died. So chances are he wasn't at that event. Now, he should have been. It would have been great if he was, because I think lots of things might have changed, but he wasn't. And so that's an example of a hallucination. And the other thing that I'd like to point out is I'm big into this context thing. So when we're in an environment and you say something like, "The Wizard of Oz is a good man, what can he do?" the Wizard of Oz is a phrase. It's a literal phrase, and it could be determined as the Wizard of Oz. It could be the book, the movie. It could be the person described in the book, or it could be my neighbour's son who likes calling himself the Wizard of Oz. And as a person, if somebody said, the Wizard of Oz is a good man, what can he do? I'd say, do you mean the book, the movie, whatever? And if the answer is yes, then you can spew out all of this stuff. You know, Dorothy and the Cowardly Lion and stuff, because that's from the movie and the book. But if it's my neighbour's son, it's all wrong. And so what's missing from AI is this level of context, so that you clarify what it is you're talking about before you continue. And if we want our machines to travel around like us, learn what's going on, and then store it, you want to know that the thing that it's storing information about is correct. Right? So if it's my neighbour's son who's the Wizard of Oz, I want to know that I'm now describing stuff about him, not about the book. Because if it's about the book, now I'm corrupting the book because I'm storing garbage in. And so I'm going to show you the actual tool, but because it's going to be difficult to do, I'll just show you a little bit of the background about what I'm going to demonstrate. So, immediate common ground, I've talked about that stuff. With pattern theory and role and reference grammar, which is the linguistic framework that I use. We'll talk about that after the break. The immediate common ground really dominates conversation. You know, you use a pronoun like he, she, it, they, here, that, here, there. All of that stuff is referring to the current context, and you can actually speak a language very easily without using a lot of complicated words. And we'll go through that after the break. And yeah, the frame problem's all solved by not trying to do too much. Last thing I'll talk about before I do a demo, because I've got like 3 minutes left.
So you've got 6 minutes.
6 minutes. All
We're
right.
aiming for 20 past
Okay.
for the break.
So since I've been here in Amsterdam, I was looking at some of the historical stuff that I haven't read for a while. And you guys have all heard of Zelig Harris, you know, very famous guy back in the 1950s. So I think he was Noam Chomsky's supervisor, and he learned about linguistics from Bloomfield. Anyway, Harris had this concept of transformations, which, as I'm reading, I think this is a really good theory. How come I've never heard of it? But what he was saying is that you start with simple sentences, and then language is built on taking those simple sentences and bundling it into complex sentences. So that's his theory. I think Chomsky stole the show a couple of years after this was written. But how it works is, if you had some facts like the man is tall, simple sentence, the party is in an hour, simple sentence, the man will go to the party, simple sentence. And then if you repackage it, you can get something like the tall man will go to the party starting in an hour. And that's a complex sentence. And what the system that I built does is it takes those simple sentences, tests them as well as in the repackaged form so that it's 100% accurate, and then we can rely on what we've just received. So assuming we do a little bit of context resolution as well. So testing's key. You know, it's not a linguistics course, but this is the world's languages according to role and reference grammar. All of the world's languages fit into this model. And that's for sentences, and if you wanted to take that sentence and break it down into a phrase, you'd use this, a reference phrase model. Historically, you think of those as verb phrases and noun phrases, but it doesn't actually work in practice. And here's how conversation works. So imagine we're putting in a fact. So John traveled to the hallway. It's not a question. So here's our immediate common ground, our current storage. Mary journeyed to the bathroom. So we're adding that to context because it's just the statement. It's not a question. If it's a question, we'll probably answer it. And notice that we're calling these elements particular names. So there's semantic relations, actor, position, predicate. It doesn't matter about the detail, but you'll see it when we actually carry on a conversation with the machine. And so basically, if you can recognize a sentence and break it into parts, what we're able to do with software is then ask questions and get the correct answers disambiguated from the system. Facebook was really keen on this concept in 2014, 2015, when Jan LeCun went to Facebook. And in 2017 we took them on, and not only did we get 100% right on their tests, which they were getting some percentage of because it was a deep learning implementation. Not only did we get 100%, but we also found errors in the training data which explained why they were getting the wrong errors in some of the cases. So that's how it works. I'm showing you a dictionary there. We'll just skip over that. And in order to build a system, I've said it's all about getting the science right, the engineering right. So for each language, if we take each of the pieces of a language and we put it into the system, and the system then breaks it down into its correct meaning, then we've got a system that we're going to be able to use for a long time. These are the pieces that go into it. This is what an example looks like. So the dog eats food, the dog has been eating food. All of that breaks down into this representation where the dog does the eating of food. And over here, we've broken it into a longer phrase. The dog that eats food. So it's a dog eats food. It's still the same representation, but in this case, dog is the thing that we care about that we're going to put into the complex sentence. So that's the principle. It's reasonably straightforward. And if I were to switch screens for the last minute before we have a break. Can you guys at home see that? Or in your office? Sounds good. Okay, so what I've got here is the meaning engine. If we put a sentence in like, the animal died. Sorry, it's a bit sad, but it's a good example. So we've got become dead, that's our predicate, and the animal is the thing that's become dead. Now, this predicate died is a one roll, so the one roll we get is animal. What happens if we go back here? And we've got the man killed the animal. So killed it's a verb, right? Died is a verb, but in this case, it's a bit hard to see, you've got the man does something which causes the animal to become dead. And you probably recognize this piece here was what the animal died means. Sorry, we'll, I can make it bigger after the break. But rather than do what the traditional knowledge graph would do, which is use the word kill as the part of the triple, what we're doing is we're decomposing its meaning so that if you were to put this into the system and then say who died, it would say the animal because it's the same representation here. It's just that we've got a causal impact.
John, maybe that's a good time to break. Is that right,
sure.
Ronald, for 15 minutes? Is that?
Yeah, so we have a 15-minute break, so we'll reconvene 35 past 4.
Great. Thanks. So, coffee time. Now there's more to come.
Good music.